The marketing division of an automobile manufacturer claims that the proportion of vehicles of a particular model that are sold by the original owner before they reach 20,000 miles is less than 35%. Of a random sample of 200 records of sales of this vehicle by the original owner, 58 had fewer than 20,000 miles on the odometer. Test the claim at a 0.05 level of significance. The claim is that less than 35% of these vehicles have reached 20,000 miles before they're sold. So this will be a hypothesis test about a single proportion. And from our study of confidence intervals and what we have already studied about hypothesis testing, it seems natural that we would just go ahead and jump right into this normal distribution and look at the hypothesized proportion, which we can use a P for, or sometimes you would see a little subscript 0, P sub 0, and that has to do with the null hypothesis. This is our hypothesized population proportion, 0.35. But we have to actually hold off a second for doing that by thinking about justifying the use of the normal distribution. We have to show that NP and N times 1 minus P are both at least 10. Since N is 200 and P is 0.35, then N times P will be 70. 1 minus P would be 0.65, so N times 1 minus P would be 200 times 0.65, which would be 130. So we have shown that both are at least 10. So we are justified in using the normal distribution to approximate these probabilities. Now, let's look at what this claim is. It says that the proportion is less than, the population proportion is less than 35%. Well, if we took a sample and that sample had a sample proportion that was actually greater than 35%, then it wouldn't support this claim at all, and there would be no point in doing a hypothesis test. Now remember, what we're doing is using sample data to draw a conclusion about a population. And if we're going to do that, then we have to take into account the probability for sampling error, which means then if we are going to reject that the population proportion is 0.35 in favor of the notion that the population proportion is less than 0.35, then our sample proportion would have to land down in this region here, where it's very unlikely that we would find a sample proportion if the population proportion is 0.35. So this is our rejection region, and we're going to need a critical value. We can find this critical value using the TI-83 or TI-84 calculator by pressing second, variables distributions. We want to use the inverse normal function, so we'll press 3. The area, the accumulated area, will be 0.05. This is a left tail test, so we will be looking for the z-value that occurs where 0.05 of the distribution has accumulated. Go down and click paste. If you're using an earlier TI-83 or 84 calculator that goes straight to this inverse normal function and gives you this open parenthesis, then the syntax order would be that area in that left tail, and then the mean and the standard deviation. And then close your parenthesis and make sure to get your commas in between. Click enter, and we get this minus 1.645. We could also find this critical value if we round to 3 decimal places. Using StatCrunch, we would do that by clicking Stat, Calculators, Normal. We would leave the mean at 0, the standard deviation at 1. And then what we want to know is, what is the z-value when we have 0.05 accumulated in the tail? So less than, this value gives us an accumulated proportion of 0.05. Click compute, and that's what the picture shows us here. So what is that value? It's minus 1.645 if we round to 3 decimal places. So this z-critical value will be minus 1.645. And our decision rule would be if our z-test value is less than minus 1.645, we would reject the null hypothesis. Now we need a z-test value. The z-test value is calculated by p hat minus p, and again, you know, we can use these little subscripts, p sub 0, to signify the hypothesized population proportion. And then that will be divided by a big square root, and that square root will be the hypothesized proportion times 1 minus the hypothesized proportion divided by the number of observations. So we would have 58 over 200 minus 0.35 divided by the big square root of 0.35 times 1 minus 0.35, which will be 0.65, divided by the number of observations, which will be 200. And that value will be minus 1.779 if we round to 3 decimal places, like we did with our critical value. We can use the TI-83 or 84 calculator to find this test value. We would do that by pushing Stat, go over to Tests, and what we want to do is conduct a 1 proportion z-test, so number 5, so push 5. Then it's going to ask us for the hypothesized proportion, which was 0.35. Then we can cursor down to x. That will be our number of successes, which this time was 58. Then our number of observations was 200. And then we need to make sure that we get the direction of the inequality in the alternative hypothesis correct so that our p-value will be correct. It was less than 0.35. And then we'll come down and hit calculate. And this gives us a z-value of minus 1.779 and a p-value of 0.0376 if we round to 4 decimal places. Now, what happened here? That value is less than minus 1.645. It's down here in the rejection region. So what are we going to do? We're going to reject the null hypothesis. And we would say something like sufficient evidence was gathered at the 0.05 level of significance to support the claim that the population proportion is less than 35%. Since I wrote it out as a proportion, then I wrote the value as 0.35 rather than 35%. Now we could find this test value using StatCrunch. If we're going to use StatCrunch, we would push Stat, Proportion Stats, 1 sample with summary. Our number of successes was 58. The number of observations was 200. Our hypothesized proportion is 0.35. And we want to make sure that we get the direction of our inequality correct so that our p-value is correct. It should correspond to what we see in our picture and what we see in our alternative hypothesis. Click compute. And here we have that z-stat value again. But we also have this p-value, 0.0376. So our p-value is 0.0376. And the significant thing about that is that it is less than 0.05, which is what we set for alpha. Again, this method of drawing our conclusion using the p-value in alpha, where anytime the p-value is less than alpha, we would reject the null hypothesis, leads us to the same conclusion. We would still reject the null hypothesis. And that is, again, because this method is exactly the same as using our critical value and test value.